Hey guys, this is Mr. Bennett, and this is Conceptual Chemistry Unit 17. We're talking about nuclear chemistry, and this is video 1 with a specific focus on radiation. Now you'll notice that I'm not actually filling in the same handout as you guys. This is my PowerPoint. I think I'll speed things up a little bit in this particular set of notes, so bear with me, and obviously you can pause the video when you get to a particular slide if you need to copy things down. Okay? So we need to do a little bit of review. The first thing we need to talk about is kind of review what an isotope is. So isotopes are atoms of the same element with different masses. Okay, so same element, different mass. And here we have an example. Notice that we have iodine. So all three of these are iodine, but on top, right, the mass, and this is the atomic mass. Okay, is different for each one, right? However, when we look at the bottom, the atomic number is the same. So why does that need to be the same? Well, it turns out, if you remember, atomic number is the number of protons, and that determines the identity of the element. So if these are all going to be iodine, of course they all need the same 53 atomic number. On the top, the actual atomic mass, which is what this is what the actual atomic mass of this particular element is, or this element, would be made up of the protons plus the neutrons. Okay, so in the case of these three different iodines, they simply have different masses because they have different numbers of neutrons in their nucleus. One thing to be careful of, these numbers up here, they are not the atomic mass from periodic table. Okay, so when you go to the periodic table, remember that those are the atomic masses, their average atomic masses, figured out by the average atomic mass of all isotopes for that element throughout the universe. These numbers here are actual atomic masses, so they tell you the actual number of protons and neutrons, not the average. Okay, so just to kind of summarize that all, in order for them to all be the same element, so for these to all be iodine, they must have the same number of protons. The protons are what are important for determining the type of element. In order to be different isotopes or have different masses, they have to have different numbers of neutrons. Okay, so that's what an isotope is. And one more thing real quick, these guys right here, remember this is isotope, these are isotope symbols. Okay, and a nifty little trick about isotope symbols is that if you put a line here, put a little minus sign, take the atomic mass of 127 and subtract the number on the bottom, that's going to give us, let's see, 74, right? That gives us the number of neutrons, because 53 is the number of protons and 127 is protons plus neutrons. So if we subtract the protons, we're left with the neutrons. Just kind of a handy trick if you need to figure out how many neutrons this particular isotope carries in its nucleus. Alright, so let's keep going here. Now we've got a little bit more review here. So the next thing we need to talk about is what is holding the nucleus together. Remember, the nucleus is really just this giant clump of positive charges, meaning protons that are held close together. And these protons want to repel against each other. They want to push against each other, and the nucleus really wants to fly apart. But it turns out that when protons get close enough, right, there's another force that will kick in and hold those protons close to each other. It's stronger than the repulsion of their opposite charges. And that force is known as nuclear forces. So we call that the nuclear force. There is another name for this. It's also referred to as the strong force because it's stronger than the repulsion. Okay, so you may hear it referred to in either way, the strong force or the nuclear force. But the point is, it's the nuclear force because it's in the nucleus, and it's strong because it's stronger than the repulsion of two positive charges pushing against each other. Okay, it also turns out that those neutrons in the nucleus, they help stabilize the nucleus as well. They help to kind of balance everything out. And it's really the ratio between the number of neutrons and the number of protons that determines how stable a nucleus is. So some nuclei are really stable because they have really nice ratios of protons to neutrons. And then you have other nuclei, other isotopes that are very unstable, things like uranium and other radioactive elements, where the balance of neutron to proton just isn't quite right, and it ends up being unstable. And that's really what we're talking about in this unit. We're talking about elements or isotopes that are not stable due to their ratio of neutrons to protons. And we're talking about how do they fix that. Okay, so what happens if they're unstable? Well, it turns out that the nucleus is going to release energy in order to become stable. It wants to get rid of that energy. Being unstable, okay, so being unstable requires a lot of energy. So as it gives off that energy and it gives off the excess protons and neutrons that are making it so unstable, it will become more stable. And what you'll often see is that a substance that undergoes radiation or radioactive decay will actually change the identity, meaning it'll go from being something like carbon to something like nitrogen, or it'll go from having a ratio of atomic mass to atomic number that's unbalanced or unstable to having a ratio that is more stable. Okay. Essentially, radioactive decay is always going to create a more stable form of an element. So the energy that's given off as this instability becomes more stable is known as radiation. Okay? So radioisotopes are just isotopes that are radioactive. In other words, they're isotopes that are unstable and that are giving off energy to become more stable. Okay? And that energy they give off is known as radiation.